to introduce our third speaker, who is, of course, our host. And I haven't got my glasses on, because I know who he is, but I better just get it. As he employs me, I better get his title right, his title of his talk right. So it's Professor Zhongyun Fan, Professor of Metallurgy and Director of BCAS at Brunel University, and our host here. And the title is A Global Renaissance of Metallurgy, the Birth of Metallurgy 2.0. I hope we're not going to get into a fight over whether it's 2.0 or 4.0. I don't know what happened to 3.0, but I can do that tomorrow if you want. But anyway, it's the new metallurgy, let's say. I think you know what they're talking about. But Fan, over to you.
Okay, thank you, Brian, for the introduction, and thank you to see you again. And here, I position myself. I invited myself to give a talk. That's the first place. Second one is I position myself in the third place to present my ideas, because I know they're going to talk about big pictures, so I reduce the number of slides as a friend, so I can talk about the substance. And the other thing was, we talked about big idea, digital twin and a physical twin, and there's another one, the brief behind is a physical twin as well. So I'm going to put some ideas into this. What does metallurgy 2.0 look like in real terms, and what we do in laboratory on a daily basis. And so lots of case studies, as mentioned earlier. That's my talk, okay? And we see, look, I'm not going to repeat all this, and just simply see, okay, metal is very, very important. It's so critical, and it's so damaging as well. And we need to do something about it. And as a key thing is here, I would like you to realize extraction and processing metals is the largest single contributor to climate change. It's more than anything else. You may think about a fossil fuel and all this. Metal extraction is the one, not others. No, you missed it. I'm going to finish the big picture to see, okay, here. We got a linear way of doing things. We extract metals. We utilize them like a one-off basis, and then we dump them. So it's linear resource consumption, which basically holding out the nature we are living in, we are surviving in. And I got this diagram here that just kind of show that is apple. This little guy is like us, what we're doing, holding out the system we are living in. And this causing big collision between two opposite things. One is, I don't know how, this is the one. The human economic activities, expanding, because we think we are master of nature, and as we conquer nature, we take whatever we want. And then this activity is expanding, and nature, of course, is shrinking because we take things inside, and they're getting hollowed out. That's the problem. So expanding economy is called a collision with shrinking nature. And that's where our crisis emerge a simple way. And as I said earlier, this is a big crisis, but a crisis always offers us a great opportunity. That opportunity at the moment is about, we see in terms of metallurgy. When you think about how we source, we formulate, and how we use our metallic resources. That's the opportunity. And of course if you do that, and globally appears to be, at least in my opinion, is a global renaissance of metallurgy going on across the whole world. It's not only academia, in industry, in government, and in the whole society, okay? This gave birth to what I called metallurgy 2.0. Earlier, Brian was joking, said, is there going to be a metallurgy 3.0 or materials 4.0, 5.0? And I just make things simple. I said 2.0 for a good reason. Sustainable, unsustainable, that's all. For 5,000 years, we are working on very simple, linear way of thinking, lead to metallurgy 1.0, which is not sustainable. Today, we realize we need to do things differently. That's what we're going to do, metallurgy 2.0. But before 2.0, the specific case studies, activities. I'll see, okay, a little bit information about Metallurgy 1.0, okay? And there was 3 historical events or discoveries which have almost molded our linear way of thinking. And I just pointed out here, and we're all very familiar. Pure metal was found in nature long time ago. And the other one is addition of tin to copper made copper much stronger. And if we hammer iron, and iron becoming much stronger, these 3 things, pure metal, addition of another element, and hammering, which almost molded our way to do metallurgy 1.0 for 5,000 years or more. And today, that's what we have. We extract metals. For pure metals, everything has to be pure to start with. That's the product. And physical metallurgy have led to so many grades of steels and 400 aluminum grades and all this. So diversified, so many of them. And the other one, mechanical metallurgy, or we call it thermomechanical processing. That's the cornerstone of metallurgical industry, which delivers all the products and materials, okay? You can see the connection between these two for 5,000 years. The general direction has not changed. That's what I call the linear way of thinking, okay? And then to further demonstrate, okay, I call it linear science here, the physical metallurgy one. And few have measured a few of this. See, pure metal here, if you got another element there, becoming, solution straightening, and then it's a defect, lie defect, and we see gray boundaries and also precipitates. That's the major straightening mechanism there. But the interesting thing here is the undergraduate courses where we learned is one by one, individually. And then what you do, to predict the strength of metallic material, what you do, you add them together. And what I call X1, X2, X3, it's written this way. That's metallurgy 1.0, eternal physical metallurgy, linear way. And E effect, there's lots of interaction between those factors. And sometimes they can be bigger. I'll tell you one example here. And we see aluminum alloy and 6,000 series. If you do this linear addition, you get about 270 to 300 megapascals. That's what you get. And recently working with Constellium, and Constellium boss sitting right behind there, and we'll be working on interaction between different factors. We'll be able to push the yield strength on industrial scale over 400 megapascals and 425 routinely, and even more. And I'll come back to this later. Okay. And linear technology. And I just see steel making, and it happened to be my first degree was about steel making. And more importantly, I was specialized in electrical arc furnace steel making. And today, that's the most favorable one for recycling. And but you look at this steel making process. We got iron oxide, got oxygen. We don't like oxygen. We want to have pure iron. So what do we do? We react with carbon. And then we produce pig iron, which is iron with carbon dissolved a few percent. It's very brittle. And then what we do? We don't like this carbon, so we blow oxygen into it. And of course, the carbon is burned out, and oxygen is up. So what do? We put aluminum, magnesium to deoxidize. And oxygen, dissolved oxygen is down. But the problem now, we end up with bigger trouble, which is oxide. And the purification process after that becoming the major problem for steel making industry, okay? There's many process. You can see this linear process, and quite often from one factory or one workshop, do one thing, pass to the next one person. So one problem creates a bigger problem for next person in next workshop, okay? That's so-called linear way, okay? Circular economy, I've mentioned so many times. I think circular economy, I don't know is something called is circular economy an economy or is ideology? But at least I would believe circular economy is our approach, okay? Like ideal gas at least, which tells you what's rising towards the future, okay? And the circular economy principles here, and normally people would see it as 4, but I added the first one, which I think is more important, living in harmony with nature. And for a long time, at least after the Industrial Revolution, we believe we are the master of the world. We conquer nature. Actually, we are not. We should be friend of nature. So we need to position ourselves right, and then you can do the right thing. And the second one is thinking systems, system approach. We need to think about multi-factors, multi-actors, and multi-stakeholders all around. Do research, that's very, very important. You cannot be linear, single-factor experiments, as a lot of physicists do, and I think we need to think much more. And with as resource, we know this, resilience through diversity. I want to mention a few things here. In nature, we learn from nature. Nature, if you go to Africa safari park, and the guy will tell you, I just cannot have lion here. I need to have other things. A critical level, and then lion can survive. So that's biodiversity, and plants the same thing. Okay, but here we think about single principal elements, alloys like steel, like aluminum, and all this. But we learn from nature is resilience can be achieved by diversity of alloy elements, and use them cleverly. Okay, of course, use renewable energy. I'm going to go back to this. I think these principles will guide us through. It's very simple. What are we going to do with the future metallurgy? And we said our long-term vision. And people always ask, can you define what's the vision? And I always say, okay, vision is something you can imagine 20, 30 years' time. What you see, you can imagine what's going on, what's the science, technology, and industrial configuration. But I also tell people, say, the things about vision, you tell people cannot prove you are wrong because they cannot get evidence to show you are wrong. They either believe it or they don't believe it. And that's a good thing and a bad thing as well. So at least I telling you the future, what we believe for metals is something like this. They should be circulated. In ideal case, no more mining, no more extraction metallurgy. People say, you're too extreme. I'm talking about future, okay, long future. In the future, I'll tell you later on, we got enough to circulate. We need science, we need technology. That's metallurgy 2.0. And how are we going to deliver from metal circulation? And as I mentioned earlier, learn from nature, circular economy. We need to use a systems approach. We need to consider multi-factor, multi-actor, and multiple stakeholders here. But overall, the three major approaches. One is for metallic materials, we said full metal circulation is a loop. The metallic flow loop here needs to be closed, which is about end-of-life recycling, and everything needs to consider a closed loop manner. And also you need to narrow down the loop. You can use less. Sometimes it's not necessary to use metals because they're so precious. And we can use high-strength material to make the demand less and slow down this process, which is about keep metallic materials in service for much, much longer. So throughout my talk, I'm going to utilize this system, either closing or slowing down or narrow. And highlight this in red here. Every slide will start with this word, so you know what I'm talking about. I'm not going to repeat myself. And also, I'm going to utilize specific cases to demonstrate how things can be done in a particular aspect. Okay. Recycling, closing loop, recycling is very important here. Recycled materials, they have two problems. One is you have inclusions, have dirts, okay? And which dirts have two sources. One is a scrap, introduce mud and all other things, okay? And the other one is naturally metal got oxide itself. It's always there. So how you deal with inclusions is a big thing. And in the past 12 years or more, and because and with LiME, we have been working on how we handle inclusions. And we found out, learning from nature, inclusion is quite a natural thing. You need to get rid of the harmful effect of inclusions, not inclusion itself. But it's a metallurgical industry, everybody, in liquid metal, filtering and all the purification process to get rid of all this. And what we found out, oxide, quite often, they are not oxide, like a solid pieces. They are nanoparticles. They stick together as a oxide film, And this can be dispersed. We developed technology called high shear. Basically, you supply very high shear rates to the liquid metal. Very quickly, a few minutes, they becoming very dispersed. And after dispersion, of course, the harmful effect for eclusions will be reduced or eliminated in some cases, or demonstrated later on. And first thing here, I see the eclusions, they're becoming very, very useful. They can supply seed for nucleation, for green farmers. And I just see here, look here, this is the real magnesium, okay? You can achieve this sort of fine and uniform mag structure by high shear only, no green finer at all. Now, I'll demonstrate that, okay, shape casting would be a very, very important way to reduce the energy consumption and CO2 emission here. And hybrid die casting, particularly for automotive, is workhorse of automotive industry, but there's a problem with this. It's cheap, fast, and high volume. Of course, it's low performance. That's the only problem. How can you make this high performance as well? And we found out if you use the high shear technology to treat the liquid metal before hybrid die casting, you get this. This is conventional. You have this centralized shrinkage porosity, have the defect bands, have a non-uniform structural distribution there, and you can produce this if you control the temperature and process right. Okay, and this what I'm showing here is the real component, tensile test piece, 6 millimeter diameter. This from here is 6 millimeters. By doing that, what you get very, very interesting here. This we worked with Zhongyun over 10 years ago. They tested the mechanical performance with this and this. The blue line here is conventional, and the red line with MC, anything with MC mild condition we called. Is this? You can see that's order of magnitude longer life with same strength, okay? Order magnitude longer, which is significant. And the other one is, okay, the high shear, once you disperse the oxide, you can recycle directly. We know magnesium alloys cannot be directly recycled because they have to send somewhere for purification. By high shear, you disperse the oxide and oxide skin and all these eclusions. Look here, 100% scrap, 100% primary alloys, and 50-50%. You cannot tell the difference at all in terms of mechanical performance. It's because we have got rid of the harmful effect of the eclusions. And the other one is, if you see, manufacturing processes. For closing loop, you have to make this process a very small number of steps. We don't want to have a very lengthy process. True casting, you can cast a very thin strip to avoid, the billet casting and then cold rolling, hot rolling, all this. You can produce a strip, but the problem with true casting, you always produce something like this. Because fast cooling, you get a very quick dendritic growth and push the solution metal becoming centralized segregation. That's one problem. By high shear, by enhancing nucleation process, okay, what you get there? Because there's no equiaxial solidification. You don't have this process pushing solution metal, so we successfully resolve the problem, centralized segregation, and refine the microstructure by 2 orders magnitude compared with this. The consequence for that is you can cast thin strip and you can direct stamp without hot rolling. So how much you get this? And unfortunately, we are not very good. But this technology should be going out there producing products. And I'm showing here just to see, okay, this is this. If you test this at different temperatures, this is the flow curve here. If you with segregations, you see this. It's random. It's nothing to do with temperature anymore because it depends on defects. So it's process. The other one is mag structure engineering. We can engineer mag structures very nicely. With a gray refiner as variable use, you get so-called rosettes, equiax, but rosettes. And you push the impurity elements like iron, aluminum, it's here very quickly. And if you promote downward arm spacing reduced, they isolate this, eventually you can disperse second phase particles. By doing this, you can eliminate or actually reduce the homogenization process for DC casting. And I can very quickly narrowing the process, okay? And I'll just show you a couple of examples here to see. And by working on interaction between solute dislocation and precipitation process by a process we call ADA, pre-aging, deformation, and final aging. We can produce at nanoscale composite materials, which basically, this composite materials is not composite, it's two different regions, high hardness, high strength, and with high dislocated density and high density of precipitates. And the other area, the white areas, lean with dislocation with precipitates. And eventually, theoretically, you should be able to push for very high strength and with very high ductility as well. And because this is about solute, pre-aging, solute, help dislocation, density to go up, and then final aging to precipitate, but keep density of dislocation high. And we confirm we can do this, okay? This is the composite materials we have produced. This region, this region, low precipitate, low dislocated density, the white area, this diffraction contrast imaging technique. So we'll be able to push normal aluminum alloy into this region here. And we are working with a STEP program to push a bit further, okay? Atomic engineering, and which is about aluminum, how you graphite aluminum, and this is 75 or 80 years old problem. What's the mechanism? And we found out actually it's very simple. Sorry. And I need to reverse the order. That's the TiB2 case. And it's about one atomic layer segregation on the TiB2 surface. It's not TiB2 itself, it's a modified TiB2, which works so well over the last 80 years. And of course, we found out earlier, said, okay, what we have learned is great aluminum copper, you got a GP zone, you got theta double prime, eta prime, and theta prime at theta, all this precipitation sequence there. And then we found out recently they are not like that. They are more like a process, and illustrated here. You got a GP zone, all this nuclear process, and then you got theta prime, it's a local structure, and you got eta prime, and I got a theta nucleation in the middle of theta prime. You got the first initial structure of theta prime, and theta prime can grow by advancing this interface. The whole lot here becoming interface. The interface is theta, eta prime, theta double prime, GP zone, rather than sequential to have all this, okay. Narrowing all this. And we found out if you got multi-components, and here we're talking about 20 elements, just illustrate the idea, you get, theoretically should have a process properly, get a amorphous material, and that's what we are working on. The other one, and you can see earlier, I think a few short one of the picture here, this is the conventional nickel-based superalloy. We reproduce this with non-nickel, with based iron, and this is a nanostructure here, similar to this, but appears under normal metrography, single phase structure here. And with 8 different elements here. They all highly concentrated. The minimum is 6 atomic percent, and the maximum 26%, okay? Atomic percent here. And this, we tested, they have very high strength. And because we got a small sample, we can only do comparative tests, and the ductility of under compression is pretty good, this early stage here. Oops. No, finally, I think very quickly, I got very quick to see this. We are working on extension of life of metallic components, and just see, we inspired by National Health Service. We're going to create a similar thing for metals, and we treat metals as friends rather than slaves, so have multiple life. And we're showing here very quickly, see, okay, this is the flow curve for fatigue. And you can see the first stage, you have dislocated tangles. Second stage, B, you got this slip bands. And you got a crack containing is the last stage here. So we create basically daily life, like a food and drink type of treatment, rejuvenating and recovering like a GP surgery and hospital for repair. And just see, with rejuvenation, we have demonstrated initially we can extend life. And the good things here, you can see we nearly doubled if we do it properly, okay? But we see, okay, I would expect that's 10 times or 100 times more rather than twice. But reason for that, we do low cycle fatigue. One cycle already damaged too much, so rejuvenization. And thick components, which we may slip bands. After 3,000, you can see lots of slip bands here. One electric pulse treatment, much cleaner. 2 pulse treatment. 1 pulse is about 0.5 seconds. Okay, that's all. And eventually, you can see the quantified here. After 3,000, you got more than half of the grease containing slip bands. 1 electric pulse reduced 30%, and 2 reduced 10%. Basically, you can recover thick components. And last one, repair. This we did fatigue. After 88,000 cycles, you got a crack. This crack can be healed completely. Just demonstrate here. This is my concluding thing. That was, allow me 10 seconds, stay, okay? And, because I have to follow the rules. I have to follow the rules, okay? Metallurgy 2.0, what I made there, is a science, technology, and engineering systems, okay, of how we meet future demand for metallic materials efficiently, effectively, and sustainably. More importantly here, by secondary metals. That's Metallurgy 2.0. And I'm not going to go through the keywords. This, I quoted Derek Robb, and latest image here. But what he best this image, he said 5,000 for Metallurgy 1.0. That's Metallurgy 1.0 is my terminology. Now, I said earlier, we only have 25 years or so to create Metallurgy 2.0. We got short time. That's a big task. Thank you very much.
I didn't think Professor Fan would reduce the level of quality, and he hasn't. He's
Thank you very much.
Brilliant talk. So lots of interesting ideas, and a little bit more digging into some of the detailed metallurgy perhaps there compared to the first 2 talks, but nothing wrong with that either way. Who's got some questions? Mark.
That's very interesting. Except at the end of your talk, you used this analogy of sick materials going to the hospital and so on. And I understand you're trying to make the medical analogy with materials. But as we know from the medical side, you don't get into the hospital until the doctor says you have to go into the hospital. And there's a cost involved. And how do you handle that preliminary cost in the area of fatigue damage or some other type of problem before one can justify, so to speak, your metallurgical hospital?
Yeah. That's a good question. Basically, I see MHS is spared analogy of AHS with UK, which is easier to understand, but it's nothing to do with sick, tired, all this, okay? But your question is about how do you know how tired the component is, how sick they are, and how much repair needs to be done. So we need to do 2 things. One is we need to develop technology for diagnosing these sort of levels, how tired they are, how sick they are. The other one, we develop technology to treat them. So it has to be parallel. That's why we use AHS as an analogy. We need to have the doctors utilizing instruments to diagnose how tired they are, and then decide how much a dose needed to rejuvenate. Okay, and so we're doing 2 things parallel. At least that's ideal.
The NHS in Britain gets quite a bad press in the US, as far as I've seen, does some very, very good things. So it's emergency. Major problem handling is fantastic. It's brilliant, and done at incredibly low cost compared to most other countries. So because of that central organisation, there are lots of problems with it. Don't get me wrong, and some of those are exposed often in the US, which often points to the NHS and says it's a bad example of state-run things. But it is brilliant at doing Dan is talking about with the fracture of materials. Now, there's a fantastically similar analogy. When we deal with metals on planes or on cars and things, we're very good at coping, or bridges, we're very good at coping with them once they've got cracks that are getting to a big size and we want to heal them. You know, the really big problems, we're actually quite good at. The thing we're no good at is the equivalent of public health, right? Giving them a bit of food and drink earlier on so that they get, and I think that's one of the cool things we've come up with is this idea that we should be kind of regularly treating them a bit like having a sleep every so often. And it turns out, and we've known this for years, actually, it never occurred to me, if you fatigue something, but you just break the fatigue every so often, the life goes up. Yeah. Well, nobody's maximised the capability of doing that with our usage. It's a brilliant idea, I have to say. Anyway,
well, thank you.
Let's go on to another question before we finish.
It's just a comment, actually, Brian, between the two of you there in terms of, I'm not suggesting the full life cycle, but certainly the rejuvenation. Rejuvenation is alive and well in the flying turbine and land-based turbine market. So you do extract under predetermined rates and bring them, probably suffering from creep damage at the time, and actually then process them and get them straight back into the field. So there are some models out there to directly link to actually show and demonstrate to, if you like, policymakers that this is something already being practiced, but it has a substantially bigger effect across the broader community.
I think this, sorry, I shouldn't jump in, but
Okay.
But it links incredibly to the servitisation that Duran and Phil were talking about. You know, if you can bring in servitisation, it's going to produce a drive to do this, because then there's somebody who's interested in not having the metal get as far as being damaged, so you can even notice it. You can do treatments before you even, there isn't even rejuvenation. You start giving them sleep when there's no problem, if you see what I mean, or a bit more food.
But I'll just add one more thing to see. The key actually is, I think your concern is about is future regionalization and recovery, how is that being done? Take the component out, go to the hospital. No, that's not that case. And in the future, if everything is well designed and major components should be isolated and subject to treatment, similar to human being here. If I have a problem with my arm, I go to hospital, you whole, not just my arm. So this is a similar thing going on. Okay, thank you.
Okay, I think we need to call it to a close. I mean, a fantastically good first session, if you don't mind me commenting as chair, with lots of really important ideas about where metallurgy needs to go in the future, needs to go for society's needs, and has in many ways, we've heard also, capabilities of delivering, not easily, but lots of capabilities, whether it's atomic engineering, whether it's digital twins, whether it's AI, and there's pros and cons of all these different ways of doing things, and we don't know how to deliver, but we do need to deliver. So there's capabilities, and there's need, and I think there's a fantastic challenge for people in this room to deliver for the world, for our communities, for the world, because the world needs it, as we've heard already. So much stuff is produced as metals, as metallurgical products. And it's not replaceable. With polymers, there's quite a lot of polymers can be replaced by other materials. There are issues of replacement of materials. Many metallurgical products are just not replaceable. We cannot sort the problem of metal pollution and energy use and climate gas emissions, greenhouse gas emissions, with replacement of metals with something else. That can't be done. We've got to make them more circular, more sustainable. Right? It's different with other materials, different with other technologies. So there's a challenge to the community, there's a potential for delivery, and it's bloody well not easy, but there it is, and I think I'm committed, and I hear a lot of commitment so far. So I think it's been a great start. Let's go and have some coffee for 25 minutes. I'm sorry, not quite half an hour, we ran over 5 minutes, that was my fault.